Hello, everybody. Good morning and welcome to the Grasland Thursdays. Grasland Thursdays is a series of webinars we organize every Thursday at 10 on various HPC topics, such as this one today on CPU architecture, which will be presented by Hadrien from IJCLab, who will introduce himself later on. But first, let me give you a little presentation of the organization team. So you have Pierre Aubert, who is with us today, a research engineer from the lab. It's a French laboratory of physics and particles in Annecy, in the French mountains. And you have Karim Azoum and I from Terratech, within the French NCC called CCFR, and with the lab of Annecy, we co-organize the Grasland Thursdays and the Grasland School. Because those 17 Grasland Thursdays you will discover are held by 9 incredible teachers who will each one of them give you webinars on their topics, introducing at the same time the program of the summer school. So what is Grasland School? It's a free summer school dedicated on programming and optimization on heterogeneous architecture, created 2 years ago by Pierre Aubert with a few people in Annecy. We, the French NCC, joined him last year to help him develop it, not only in Annecy, but also in 12 satellite sites among 4 countries. So last year, those satellite sites helped us reach more people by broadcasting the school live in their locations. The summer school had a 2 weeks program, 1 week on CPU and 1 on GPU, but everybody was free to choose the courses they wanted to attend, thanks to our a la carte option. And we finally trained over 500 people, and everything is now available still on replays on our website and YouTube channel. I will give you the links later on the chat if you want. And you can access it whenever you want, but obviously, everything is in French. So this year we're going European, so everybody will be in English, like this webinar and the summer school of this year. You have various ways to attend the school, as you'll see in the video I'm going to launch for you. And also, we invite you to be part of the team and become a satellite site yourself if you want to host the school at your place. We are able to provide you everything, all courses, containers, access to the teachers, and also to connect you with our growing HPC community. So let me now show you the video, and then we'll go back to the webinar.
Do you sometimes feel limited by your resources or unsure how to maximize the potential of your HPC resources? Imagine a place where collaboration, creativity, and learning converge with high-performance computing. Welcome to Grasland School 2025, Europe's leading summer school for HPC. Taking place from June 23rd to July 4th. Over 2 weeks, students, academics, and industry professionals from across Europe will explore the frontiers of programming while building a vibrant community. Together, we'll discuss programming and optimization on heterogeneous architectures, highlighting their respective characteristics and limitations. You'll have a unique opportunity to explore generic optimization methods, as well as the latest technologies and languages for achieving optimal performance. The school is free and open to everyone, and you can participate in person in Annecy, France, with the teachers, at one of our satellite sites in Europe, or online via our live streaming. You can choose from an intensive program or a la carte courses to develop your skills at your own pace. With the first week dedicated on CPU and the second on GPU architectures, you will study computational accuracy, vectorization, parallelization, compilation, memory profiling, unit testing, and the various programming languages C++, Fortran, Rust, Python, and Julia. In addition, we will study the MPI, OpenSHMEM, OpenMP, TBB, EVE, Kiwaku, Sycl, Thirst, CUDA, OpenACC, Vulkan, NumPy, Number, QPy, CU-numeric, JAX libraries and Legit, as well as computation with PyTorch and TensorFlow, and the G++, Clang++, NVC++, NV Fortran, G Fortran and DPC++ compilers. Throughout the course, you'll discover and use profiling tools such as Valgrind, Perf, Macau, Nsight, Malt and NumaProf. Each session leads to a practical challenge, the simulation of Gray-Scott's diffusion reaction, which tries to describe how a chemical reaction evolves over time. Simple to understand, but complex enough to push the limits of optimization. Thanks to our specially designed Docker containers, you'll have access to a complete working environment to follow courses and exercises on your laptop or supercalculator. Throughout the program, you'll be guided by a dozen expert instructors, leaders in the field of programming and HPC. You'll have the opportunity to ask questions and chat with them live on Discord, so you can tailor your learning to your needs. Join our growing community of over 500 users to find answers, exchange ideas, take on challenges together and build bonds that will last well beyond the program. You can also join the Gray-Scott School European network of satellite sites, not only to attend the courses, but why not become a satellite site yourself and host the school in your location? You just need to provide a room, a contact person, and access to computing resources. We'll provide courses, tools, and Docker containers for a seamless learning experience. Gray-Scott School is free and open to all. It's your chance to master advanced programming and optimization, engage with a growing European HPC network, and push the boundaries of technology and training. You can kickstart your journey now by joining Gray-Scott Thursdays, a free webinar series previewing the school's courses. Don't miss out. Register today to attend, whether in person in Annecy, France, or at one of our satellite sites in Europe, or online via our live streaming. Gray-Scott School 2025, where HPC meets your potential.
So thank you for watching this video. If you have any question regarding the school, you can ask them in the Q&A. And Pierre, Robert and I will be glad to answer you. Thanks for listening to me, and now it's time to give the floor to Hadrien for the webinar on CPU architecture. Hadrien, it's for you.
All right, thanks for the introduction. So my name is Hadrien Grasland. I work at IJCLab, which is a particle physics and astrophysics laboratory in the south of Paris. In this lab, what I'm doing is I'm a software engineer with a specialization in the tuning and optimization of software performance, basically doing more work given the same hardware resources or doing the same work with less resources. And today I'm going to tell you about CPU hardware architecture, which, as you will see in a subsequent webinar, is actually also quite close to GPU hardware architecture. So even if you think that CPUs are not interesting these days, you should pay attention to this talk. First of all, I should define what I'm talking about when I say architecture, because there are actually two different things that people can refer to when they say CPU architecture. They may be talking about instruction set architectures, such as x86, ARM, or Power, and they may be talking about microarchitectures, such as Zen 4 or Granite Rapids. These are not the same thing. The instruction set architecture, or ISA for short, is a contract between the binary code of an application and the CPU that this application is running on. It tells you there are these instructions, they are encoded using this set of binary numbers, and if the CPU sees this particular instruction that it's going to do, the instruction is going to have this particular effect. So this is public knowledge. You can find it on the website of the CPU manufacturers, and it's shared across a huge number of CPUs. We don't have that many different instruction set architectures in common use, at least in HPC. Instruction set architectures are backwards compatible, and they change very slowly, only via extensions, where you you just add new instructions, you almost never remove them, even if an extension can technically be removed in the far future if it's not used anymore. But this happens very rarely. In contrast, the microarchitecture is the hardware implementation of the instruction set architecture. So this is half secret, like some details are public, some are not. And the implementation can change across generations of CPUs and even across multiple CPUs within a single generation, if we are talking about quantitative parameters like the size of the caches. There is no compatibility guarantee on the microarchitecture, and because of this, it is able to change a bit more quickly than the ISA. So if it's partially secret, it's quite a bit more variable across CPUs, why do we study microarchitecture? And the reason is that it lets us answer performance questions, which the ISA says almost nothing about. If you are interested in how many operations you can compute per second, or what changes you should carry out in your program to improve your data access latency or throughput, then you need to study the microarchitecture. The ISA alone will not give you this information. Furthermore, even if the microarchitecture varies quite a bit, the variability is actually quite manageable in practice. Because the qualitative design choices, like whether you have caches, how many layers of caches, and so on, are very stable. And even the orders of magnitude of the tunable parameters, like the size of the L1 cache, change quite slowly over time, which gives you lots of time to adapt. And even when you want to write programs that are performant on multiple ISA, you will find that even implementations of different ISA turn out to be quite similar in practice, mostly because, the CPU manufacturers took decisions in similar times, having access to similar technologies, and unsurprisingly, they ended up making similar choices. Now, in the remainder of the presentation, I'm going to cover some particular microarchitecture topics that are highly relevant to software performance. And I am going to start with one first topic, which is memory access. To introduce this topic, let me take as an example one compute server, which is available to a physics team in my lab. And let's ask ourselves how fast this particular server can handle single precision floats at the floating point numbers at the CPU level. So we can consider two different metrics. We can consider at which speed it can carry out floating point arithmetic operations like additions and multiplications. And if we do the computation, we will find that it computes 8.2 10 to the power of 12 single precision operations per second if you use it optimally. On the other hand, if we consider another metric, which is how many floating point numbers, still single precision, we can transfer from CPU to RAM or back per second, then we will find 1 10 to the power 11 floating point transfers per second. And we can actually compute the ratio of these two numbers. And this tells us that on this particular system, if you are running a program that does less than 80 floating point operations per number that it loads from RAM or stores to RAM, this program is not limited by how fast the CPU can compute arithmetic. It's limited by how fast floating point numbers can be transferred through the interconnect between the CPU and main memory. And I don't know if you fully realize this while watching this talk, but 80 operations per memory transfer is huge. Most of your programs, if you look at them, they sometimes load multiple numbers per computation. So obviously, if every data was loaded from RAM, we would always be limited by this bandwidth. And if you're thinking, yeah, but the hardware designers are clever, they will save us from this. Not this time, I'm afraid. Whatever metric you're looking at, the gap between compute performance and memory performance keeps getting worse over time. And I have linked here to a more in-depth presentation by the author of the BLAS and LAPAC software. So the obvious question then is, okay, my memory is slow. It's going to be a bottleneck unless I take some precautions. Can I have faster memory? And the answer is yes and no. You can have faster memory, but only if you accept to give up on the idea of having one single memory that your program is interactive with. That's because when you design any kind of computer storage in current technology, you need to balance between several concerns, like whether it's able to preserve data when the computer is powered off, how fast it is in terms of latency when you ask something, how long does it take for the result to come back, in terms of bandwidth, how many data can you transfer per second. You also have a trade-off between performance and energy efficiency. Basically, the more performant your memory is, the more energy it will consume for a given task, which is a problem for any computer that tries to either run on battery or save on electricity bills. There's also a trade-off between performance and density, which is how many bytes of data can you store per cubic meter. And finally, all of these also are in a trade-off with price. If you have memory that's non-volatile, super fast, energy efficient, and ultra dense, it's going to be super expensive and you're not going to buy it. So the way we resolve this is we combine multiple memories. And if I look further into the system that I have presented to you earlier, then we see that actually it does not have one memory. It has each CPU core has access to many different memories. First, we have registers. If we are doing vector processing, we have 16 of them, which can store each 32 bytes of data. We can access them for our purpose. We are going to consider infinitely fast and with unlimited bandwidth. These are the fastest memory we have access to. But as you can guess, if you compute this number in your mind, you have less than 1 kilobyte of data in there. So that's not going to be enough for any serious computation. Then we have the level 1 cache, which can store 32 kilobytes of data. It takes a bit more time to be accessed, but it's still not so bad. And you can load 2 SIMD vectors per cycle and store 1 per cycle. So that's already one performance limit if you're doing lots of memory accesses from the L1 cache. Then you have the level 2 cache, which is still specific to a CPU core, but it's much larger and it's slower, both in latency and bandwidth. Then you have the level 3 cache, which is shared between CPU cores. It's again even larger. And because it's shared, you can have patterns where some cores are using more last level cache than others. That's okay. However, you must bear in mind that here this latency estimate is an approximation, and real CPUs may have some penalty when a CPU core accesses some L3 cache data which is far away from it. I will not get into the details of this in this talk. As you can see, we do not lose bandwidth, we only lose latency, but latency can be a problem. And finally, we have main memory, which is typically on particle physics systems tuned at 2 gigabytes per core. The latency is of the order of 100 cycle per memory access. And you can see that there is quite a big drop from the last level cache to main memory, which means that parallel operations are very likely to be limited by memory bandwidth if they do not manage to fit the data they most frequently access in the last level cache. And finally, we have all the non-volatile storage, which I put here for reference to show you that it's enormously slower, which means it's very easy to be limited by the access to data from storage device. And if you have a network, it's even worse. So as you've seen, caches are essential to get software that's limited by arithmetic performance and not by RAM performance. So how do we make use of CPU caches? There are a few principles that we should keep in mind when designing software that tries to use CPU caches efficiently. The first principle is spatial locality. To simplify the hardware implementation, CPU caches do not work with individual bytes of data. Instead, they work with aligned chunks of typically 64 bytes. On some CPUs, it's 128. That's only a factor of 2 change, so it doesn't majorly affect this discussion. The fact that data is manipulated in such large chunks means that in your software data structure, you should group data which is used together in memory. Like you should not have big data structures where you're only going to use a few fields of the struct, because even if you're only using a few fields, the CPU is still going to fetch a large chunk of the data structure for you. And this means in particular that you must be careful whenever in your program you have an array of data structures. You must ask yourself, okay, if I'm going to process this entire array, am I going to use every field from every struct each time? And if not, it might be a good idea to turn to a different data layout where instead of having one array of structures, you instead have a structure where each member is an array of members. Then we have another issue, which is temporal locality. So caches, as you've seen, are not infinite. They do not have infinite size, far from it. And this means that when you access some data from RAM, the cache is going to keep it automatically, but to store it is going to flush some data which has been fetched into the cache before. And the way it works is that a new cache line will replace the cache line in the cache that you have used the least recently, mostly. And what this means is that if you have some data that you are going to use multiple times in your application, you should not wait too much between two uses. You should not use too much unrelated data before coming back to this data. Otherwise, all the new data that you have used after that will have replaced the data that you meant to reuse, and your cache will not be effective at reducing the data access latency next time you need this data. And this means that, as we'll see in other courses, you need to change how your loops over two different data sets work, for example. Finally, as a general principle, you should aim for your program's data access pattern to be as close as possible to reading every byte of memory from a certain starting point to a certain ending point. Each step you take away from this simple model will cause all kinds of issues with things such as hardware prefetching, associativity, the TLB. I don't have time to cover all of these topics. But basically, linear access patterns are the hardware optimum. They are much faster than any other memory access pattern with holes in it. And you can reduce the damage when you need to do a nonlinear access pattern. But if you can rework your program so that it performs a linear access pattern, it will always be the best option. And finally, when your program has multiple threads, be careful with writes to shared memory, which are subsequently read by other threads. These operations are costlier because the way CPU caches work is that there is kind of reader-writer lock for each cache line. So at any given point in time, one of your CPU core can have write access to a cache line, or any number of CPU core can have a read-only copy. So any write you commit to shared memory leads to the caches of all other CPU cores for this cache line being invalidated, which means that the next access will need to go through at least the last level cache and possibly main memory. So basically, the message here is, if you do multi-thread applications, try to make as much of the shared state as possible read-only. Do not rely on multiple threads frequently writing to share dataset that are read by other threads. That's it for memory accesses. Now let's turn our attention to the actual execution of computation. And as we are going to see, modern CPUs have many different facilities for doing lots of different work at the same time, and mastering all this concurrency and parallelism is key to achieving good performance on modern CPUs. The first optimization that CPUs do is pipelining. So the general idea of pipelining is that if you take the process of executing any CPU instruction, you can typically decompose it into multiple independent stages. Like, for example, you will first need to load the instruction from memory. Then you will need to decode the binary format to understand which hardware instruction you're dealing with. If the instruction has input data, you will need to load it. If there is a computation to be done, you will need to do the computation. And finally, if there is some output data to be stored to memory, you will need to store it. And all of these steps are carried out by specialized hardware inside the CPU, which means that all these hardware units can potentially work independently at the same time. And the idea of pipelining is this. Instead of fully processing one instruction, then fully processing another, we can overlap the execution of different instructions. So we can start fetching a first instruction. Then while we decode this first instruction, we fetch a second instruction. Then when we load the input, we decode the second instruction, we fetch the third one, and so on. And in an ideal scenario, we can get to the point where all our pipeline stages are running in parallel. And this will speed up our instruction execution, at least the throughput, by a factor which is equal to the number of stages in our pipeline, which in real-world CPUs is typically of the order of 10 or 20 pipeline stages. So that's quite a big speed up. However, it's not that easy. There are a few things that we need to take care of, which will take us away from this ideal execution. The first problem that the CPU needs to deal with is branching control flow, like if you have if-else statements, if you have loops, if you have virtual methods. So to Lionel, decode instruction means that, when you fetch instruction, you fetch a bunch of numbers from memory, and the CPU needs to do some processing to determine that this bunch of numbers means add the number in register R1 to the number in register R3. So that's the decoding process, turning from the binary format to the actual logical instruction. So back to our pipeline hazards. So as I said, anytime we have code that can take different paths, we have a problem in pipelining design, because now we are trying to fetch the next instruction of the program before we know what that instruction is. Because in order to know, we would need to wait for the outcome of the branching instruction. We would need to know whether the Boolean condition to the if else is true or false. And we could wait, but that would be very costly. We would that's called a pipeline flush. So CPUs do not want to do that. So instead, all high-performance CPU designs go for a different path where they try to predict which path the code will take, and they will speculatively execute the code, assuming this path has been taken, but without committing any result to memory at this stage. And finally, when they know the path that the code has actually taken, then the CPU will decide whether results can be committed to memory or whether the initial guess was wrong and all the work that was done previously must be thrown away and started over. And so what this means is that your code must have a pattern that's sufficiently predictable by the CPU, because every time the CPU guesses the control flow of your code wrong, you will pay a big penalty due to inefficient pipeline usage and ineffective instruction execution. There is also a problem with data dependencies. Like, for example, if in your code you have a memory store followed by a memory load, then you need to make sure that the load is not from the data that's been stored. Similarly, if you have an addition that depends on the result of a previous addition, you need to wait for the result to be available before you can carry the second addition. There are all kinds of tricks that CPUs can play to try to reduce the cost associated to data dependencies. But ultimately, all these tricks have their limits. And if you have long chains of instructions which each depend on each other, it will be a performance issue. So you need to be careful with those. How does the CPU make predictions, asks Lionel. So it's not completely random, actually. First, there are heuristics. Like typically, if you have a branch that goes back in code, it's often taken because it's typically done in loops. Whereas if you have a branch that goes forward in code in your assembly, then it's typically not taken. So the compiler can lay out your code in memory to make these initial guesses of the CPU right. After that, the CPU also uses the history of previous branching outcome to decide what is the most likely outcome of the next branch. Like if you have often taken a specific condition for if, then if you have a certain if in your code that has often had a true condition, then the CPU will start making the guess that most likely next time the condition is going to be true again. So there are a number of heuristics, but yeah, ultimately, if you are doing things like if-else statements with a random predicate, you are going to pay the wrongest penalty many times. So one trick that CPUs play to keep their pipelines filled is out-of-order execution. So to understand this particular trick, you need to know that unlike in my schematic at the beginning of this section of the course, not all instructions are the same. Some instructions have input data, some instructions do not have input data. Some instructions load data, but from various sources, sometimes from the L1 cache, sometimes from RAM. And this means that instructions will have different latencies. They will take a different time to produce a result. And again, our CPU does not like to wait, so it's not going to wait for the result of an instruction to be available before starting the next one. So what the CPU is going to do instead is it will keep starting new instruction while waiting for the results of the previous instructions. But there is a limit to this because each instruction that the CPU has in flight consumes some internal resource in the CPU. And this means that if your code has too many high latency instructions, at some point the CPU will need to wait without starting new instructions and performance will drop. And the thing to keep in mind here is that if as soon as you are using a CPU which is not a general purpose CPU, like which is targeted at embedded hardware like cell phones or cars, or if it's an HPC specific CPU like NVIDIA Grace or Fujitsu A64FX, then these CPUs have a smaller limit to how many instructions they can have in flight, which means that you will hit the penalty for high latency instructions more easily on those CPUs. And this means that as soon as you target a CPU which is not general purpose, you need to be more careful about this concern that you normally would on a general purpose CPU from Intel or AMD or ARM. So how can you reduce the latency of your instructions? First of all, you need to be careful with accesses to high latency memory, which means that, as usual, you want to have as much of your program data to be resident in a fast cache, like level 1 or level 2 on x86. You don't want to pay the latency of going all the way to the last level cache or worse to RAM. You also want in your code to avoid dependency chains, which are instructions that depend on one another. So I mentioned this earlier. Here are some examples, like if you are doing the sum of a certain number of numbers and you implement it in the naive way, like you sum A and B and then you add C and then you add D, then you will have a dependency chain between all the successive additions. If you index an array by an index that you get from different array, again, you introduce dependency chain because first you need to compute the memory address of this element of array Y. And then with that, you can load the data and then you can use this data to compute the address of the element of array X. So again, dependency chain. And similarly, you should avoid deeply nested structs that contain pointers that point to different structs that themselves contain pointers. That's a common concern with object-oriented programming. As you've seen before, a CPU actually does quite a bit of work each time you execute a new instruction. And this raises the question, could we perhaps amortize this work by doing more work per instruction? And I'm glad you asked, because that's exactly what single instruction multiple data, alias SIMD, is meant to do. So if I go, for example, on x86, all modern CPUs have an instruction called add PS. And what this instruction is capable of doing is it's capable of taking 4 single precision floats and sum them with 4 other single precision floats with one single instruction. As you can imagine, this can lead to quite a large speed up because now you can do a lot more work per instruction, so your program needs to have less instructions for the same work. On the other hand, unfortunately, SIMD as a programming paradigm is quite hard to use for many reasons. First, only few operations are supported in hardware for SIMD execution. a lot less than for scalar operations that only manipulate one pair of inputs, for example. There are all kinds of weird limitations, like you can have operations that are available for integers but not for floating point numbers, or that are available for 8-bit integers but not 16-bit integers. These weird limitations are highly specific to a given instruction set architecture, which means that making SIMD programs that perform well on a wide range of SIMD architectures, like on both ARM and x86 CPUs, for example, is difficult. And even within the boundaries of a single instruction set architecture, SIMD instructions are the fastest evolving aspect of an ISA, which means that you will have many different extensions that you will want to consider to support. Like, for example, on x86, you can support the oldest vector instruction set SSE, or the slightly newer one AVX, or the even newer one AVX512. Each time you go to a newer instruction set, you can target less CPUs. And this means that a program that aims to cover all x86 CPUs from the dawn of time will need to have a version of each computation for each instruction set. This can be even more complicated, like in the case of ARM, where there are two different SIMD instruction sets which have completely different logic, like one called Neon and one called SVE. And unlike in x86, there is no guarantee that if a CPU supports the newer instruction set, it also supports the older one. Finally, SIMD instructions are extremely sensitive to the layout of data in memory, which means that anytime you start building some abstraction around data, like some encapsulated object, you need to be very careful because you're possibly making your work harder at the time where you want to do SIMD. Typically, in SIMD, it's a good idea to only have abstractions over collections of data and not individual data elements or data points. We can discuss more details if you want later in the Q&A. So how do you choose to use SIMD? Does the compiler decide for you? It can, but it only manages in very simple cases, first. And second, it cannot target all SIMD instruction sets because they are not available on all hardware. So you need, at the very least, to tell your compiler which CPU model you are targeting in order to get optimal code generation. And if you want to target many different hardware, it's more complicated. You need to use something like the GCC function multi-versioning extension. And then you need to shape your code into one of the few patterns that the compiler knows to turn into SIMD, or you need to use an explicit SIMD programming model, which is the path I would personally recommend. We will cover both options in more details later in the school. So we've seen that we can run some instructions in parallel via pipelining, but actually CPUs have options to run even more instructions in parallel. And here I have shown the three most common options, where the ones on top are cheaper to implement in hardware, but harder to use as a programmer. And the one at the bottom is hardest in hardware, but easiest for the programmer. So the first way a CPU can execute multiple instructions at the same time is via superscalar execution. The idea is that now, instead of being able to process, so if I go back to my pipeline image earlier, instead of being able to do one computation at the same time, now let's say your CPU is now capable of doing two computations at the same time. This can work as long as your program contains independent instructions. What do I mean by this? Let's say you want to sum four numbers. You can do it in two different ways. The naive way boils down to summing numbers A and B, then adding C to the sum, then adding D to the sum. If you write your computation like this, then the program does not contain independent instructions. You have three sum instructions that each depend on the result of the previous one. If, on the other hand, you write your computation like this, like sum A and B, sum C and D, and then sum the two, then here you see that you have two independent sums followed by a third sum that depends on the results of both previous sums. And this brings us back to a theme which has been recurring in this talk, which is that you want to avoid this sort of dependency chain pattern if you want performance. It's faster to have this sort of pattern where the instructions of the program are made as independent as possible. I can show you later on how that's done if you're interested. One step up in complexity in hardware, we have simultaneous multithreading, which is most well known by the commercial name of Intel, which is hyperthreading. So the idea of hyperthreading now is that, okay, so your hardware has multiple compute units per core, as in the superscalar model. But now the CPU is capable to share those units between multiple threads. What this means is that if you write your program as a set of independent threads that do different things and thus exercise different compute units, then you are able to use these different compute units better without working on having more independent instructions in your program. So what's that good for? As soon as you have properly tuned your program, it's mainly good for situations where you have high latency memory access from one thread. Then you know that instead of waiting for this, the CPU can hand over to the other thread while waiting for the memory access. It's also good for scenarios like blocking I/O, where you have a thread that's going to do nothing for a long amount of time, and then at some point it's going to wake up, and when it wakes up, you want it to wake up as quickly as possible. On the other hand, multithreading, hardware multithreading is bad in situations where you have well-optimized threads that do not do high latency operations and all do the same thing, because if they do the same thing, they are going to put pressure on the same compute unit, and then they are going to fight each other for the compute units, the cache space, and so on. And at best, you will get no speed up, and at worst, you will get a slowdown due to the increased pressure on the shared resources like the cache. So to summarize, hyperthreading is something that tends to work perfectly for an optimized code and which works less and less well as you optimize your code for computational programs that do not have many of these operations. Finally, we have multi-core, which is the most expensive in hardware, but the easiest for programmers. So here you still have a program composed of multiple threads, but instead of these threads sharing the same compute units, now they each get their own compute units. That does not mean that they are fully independent. They still share some resources, like as I mentioned earlier, different CPU core share the last level cache. They share also the memory bandwidth, the storage devices below that, and so on. And so you still need to be careful in order not to be bottlenecked by those shared resources. But it's easier to get good performance out of multi-core than out of multi-threading because you have less shared resources. So if I put all of the different hardware concurrency and parallelism mechanism that I have presented earlier into a nice table, so this is what we get. So you have pipelining. To get good pipelining, your code needs to have predictable control flow, which means that you must be careful with branching control flow at the bottom of your hot loops. You have SIMD, the single instruction multiple data, also known as vectorization. To use it, your program needs to use special instruction. In easy cases, the compiler can generate them for you. Many times you will need to write them yourself. You have superscalar execution, which is the ability to execute multiple independent instructions at the same time within a single CPU core. You have multi-threading, where your program has different threads and for multi-threading to work well, your threads need to have high latency workloads, basically. And you have multi-core or different workloads, that put pressure on different compute units. And you have a multi-core where your program is still composed of threads. And now the only constraint is that these threads must not put too much pressure on the shared resources like the last level cache or the memory bandwidth. I have highlighted using colors how much gain you can expect to get locally in the code region where this is the limiting factor. As you can see, some things are more important optimization targets than others. And one thing you will notice for SIMD is that typically the benefit you can get depends on the size of your individual data elements, which means that SIMD nudges you towards using smaller width integer or less precise floating point numbers. And here is a rough estimate of how much work you need to do in order to correctly use this or that aspect of the CPU. As you can see, multi-threading is basically garbage for computational purposes. It's rarely worth optimizing it will rarely give you good performance when you optimize for it. I mainly mention it because it can hurt your performance, and then you may want to disable it using an operating system facility known as CPU pinning. I don't have time to go into details of all sections in this table, so I will leave you there, and if you have questions, do not hesitate to ask them at the end of the webinar. And so a few other topics. Let's talk about floating point arithmetic. Here you need to know that at the hardware level, not all floating point operations are the same. There are some operations that are privileged in the sense that the CPU, a typical CPU, can perform 2 of them per cycle. These are addition, subtractions, multiplications, and fused multiply add, which is the combination of a multiplication and an addition or subtraction without intermediate rounding. So these are very fast, and if you do them in SIMD, the SIMD operation is as fast as the operation on one single data element. Then you have division and square roots. These are still implemented in hardware, but they are more complicated, so they take more time to execute. And furthermore, they do not scale as well when you do SIMD. Typically, you will find that for the smallest vector width, you get some benefit, but the benefit does not grow linearly as you increase the width of your SIMD vectors. And finally, you have all the so-called transcendental functions, which are even slower, and unless you do something special in your program, will never be carried out using SIMD, which means that you must compute exponentials, logarithm, and so on, one by one. You can actually use SIMD for this, but then you need to use special SIMD libraries, which themselves will need to use hardware instructions which are not particularly fast, like gather. So basically, the more you rely on this sort of computations, the less benefit you will get out of SIMD optimization. The consequence of this is that obviously you should prefer the simple operations near the top of this table. When you do need to compute some kind of inverse, square root, or 1/x for division, instead of, for example, dividing many numbers by the same denominator, you will want to compute the inverse of the denominator and multiply by that, because then instead of doing lots of divisions, you will end up computing one division to compute the inverse of the denominator, and then many multiplication, and that will be faster and scale better with SIMD. And one particular vigilance point is trigonometry, at least in the code that I deal with, where people often do stupid things like computing the sine of the arctangent of x and y. Don't do this. Remember the trigonometry you learned in math in high school. You can just compute x over the square root divided by the square root of the x squared plus y squared. And because of the enormous performance difference between these operations, it will be much faster. Finally, there are other operations which are slow in hardware for no obvious reasons. I mean, if you know a bit about hardware, you can guess that they would be slow, but most of the time, the first time you encounter them, it will surprise you. Some examples that I will quote from x86 CPUs are subnormal floating point numbers, which are really tiny numbers that cannot use the normalized IEEE 754 representation. These are typically encountered in physical or chemical simulation that feature some component of spatial diffusion and exponential temporal decay. And on Intel CPUs, multiplicative operations on subnormal numbers can be 100 times slower than the same operation performed on normal numbers. That's a big vigilance point. On other CPUs I could test, the impact is less. I will talk more about this during the talk from next week. I will share some data with Vincent Lafage. Another vigilance point on Intel CPUs is if you have reads and writes in quick succession that are separated by a multiple of 496 bytes. That's due to the way CPUs check whether 2 pointers point to the same memory address. It's a bit complicated, linked to address translation. I will not go into the detail. But it's sufficient to say that if you are reading from one line of an n-dimensional array and you're writing to the next line, for example, you may be in trouble if the line length is a big power of 2. And other typical gotchas include integer modulo, use of complex addressing mode, and x86, and so on. So these, I mean, you can over time learn some of these, but you are unlikely to know about all of them from the beginning. So here is my suggested strategy to find them and then know how to resolve them. So if you are using Perf as a profiler, or equivalently Intel vTune on Intel CPUs, Perf has something called annotate, which can show you the assembly code of a function with slow instructions highlighted. You will want to check this periodically on your program and ask yourself, is it normal that this assembly instruction takes this proportion of the function execution time? And I mean, that's not an easy question. Like, you need to know a bit about your microarchitecture, but over time you will get better at this and you will be like, hey, wait, it's not normal that I'm spending so much time writing data here because it's in level 1 cache. And then you think, oh yeah, but that's because of this 4K aliasing stuff. On Intel CPUs only, unfortunately, you have very detailed performance counters, and you can use these to look for performance events that occur frequently, which mean that you have a bottleneck on a certain aspect of the hardware, and you want to check the list of those bottlenecks by enumerating them using tools like the vTune top-down analysis or the top-left command line tool. And you will want to ask yourself, is it expected that this is a bottleneck? And if not, you will want to study the vendor documentation to know what this hardware performance counter is measuring and what it means when this performance event occurs frequently. And as a more general recommendation, all reputable CPU manufacturers publish optimization guides. You will want to get those optimization guides for all the CPUs that you are targeting and read them carefully. They are full of precious information. In a typical code, the thing you will want to focus on is first, be very careful about any kind of floating point computations. Compilers do not perform a large amount of optimization on those computations because since floating point math is not associative, many program transformations will change the program result. And sometimes it's actually for the better, but it could be for the worse. It's very hard for the compiler to know whether changing the rounding of some operation is safe or not. And if the compiler gets this wrong, it breaks a property of your code called numerical stability, which means that you will get numbers at the end, but these numbers are garbage. They don't mean anything. So as a result, compilers are very conservative around optimization of floating point computations, which means that many of these optimizations are your responsibility. You will want to be extra careful inside of innermost loops, loops nested inside of loops, which have many cumulative iterations. Here, you will want to pay most attention to all the points that were discussed during this presentation. You will want to have high spatial and temporal locality in your level 1 cache and lower level cache if necessary. You will want to have linear memory access patterns. You will want to have as little branching as possible. And when you have branching, you will want to keep it predictable for the CPU. You will want to be careful also with polymorphism, which to some degree can be seen as a kind of branching, because it breaks a very important compiler optimization called inlining, which itself enables many other optimizations. And it adds indirection, which means dependency chains. And as you've seen before in this presentation, dependency chains are a problem. In general, when you have dependency chains in your code, you will want to break them down into more independent operations. And finally, if your program does lots of I/O or thread synchronization, is going to do lots of system calls. And what you need to know here is that system calls involve very expensive CPU operations. We are talking about an overhead in the microsecond range, so thousands of CPU cycles. And it keeps getting worse as more and more CPU security vulnerabilities are found. So this means that it's very important to make sure that you call into the operating system as few times as possible by using coarser grain operations like coarser grain IOs that fetch bigger data blocks, coarse grain thread synchronization. You don't synchronize every computation, for example, but every 10 or 100 computation or 1000 computations. So to conclude, modern computational chips, both CPUs and GPUs, are very complex. They have many mechanisms that affect runtime performance. And because of these mechanisms, some kinds of code are easier for the CPU to process than others. And it is your job, unfortunately, as a programmer, to work with the CPU, consider it as your ally in the quest for performance, and do not work against it. So this means that some aspects of your program design must be, you must design your programs while paying attention to what CPUs are good at, what they are bad at, and what the code needs to do in order to leverage all the available CPU resources. The good news is you actually don't need to sacrifice portability for this, because what I've been telling you about in this presentation is mostly common between x86 CPUs, ARM CPUs, Power CPUs, GPUs even. They all are designed using the same principles. They follow the same qualitative design decisions, like they all have caches, they all have superscalar execution pipelines. And the main differences lies in the orders of magnitude, like how much cache you have per CPU core, for example, how wide your SIMD instructions are. And these points are relatively minor and can be covered if you use the right abstractions and tunables in your application in the right places. So to conclude, here is a big bunch of resources which will allow me to start answering the questions. So this first book is a highly recommended first read if you have never done CPU microarchitecture before and you want to know more about how a program can be tuned to use a CPU microarchitecture before. You will want to check the documentation that's provided by your CPU manufacturers and also by independent experts. And here are some news outlets from that keep you in touch with what's new in the latest CPUs and GPUs. So someone asked, where can you find the information about the CPU speeds and registers? Some of them you will find in the vendor documentation. The vendor considers a trade secret, so they do not tell you about it. On the other hand, you can find that independent experts have worked on it and found out, Wikichip is a good compendium of knowledge for slightly older, or not the latest, but CPUs from Intel and AMD from a few years ago. Microoperations.info gives you the best case latency and throughput of all CPU instructions from all Intel and AMD GPUs, and is a super useful resource when you're working at the bottom of your loop nests. Concerning the story about reading and writing data separated by 4K, my recommendation is to, I explicitly pointed this out as an example of counterintuitive hardware behavior. So I do not expect you to necessarily remember this or think about it all the time, but when you are evaluating the performance of your code, keep looking at the microarchitectural analysis of tools like Intel vTune, and ask yourself, is it normal that I'm using this aspect of the microarchitecture more than another? Why is this performance critical event happening many times, and so on? Use your profiling tools, basically. And then you will find out about this 4K aliasing behavior, among other things. And why do I know, actually, when looking at my performance monitoring counter, that it's this behavior? Also because I have checked the documentation from Intel, which tells you about it. So also read the optimization guide from the CPU manufacturer. How do I choose to use SIMD? I believe I have answered this. So in easy cases, the compiler does it for you, but you need to specify which CPU you are targeting for optimal performance. And otherwise, you need to use the SIMD instruction yourself. And you have several abstraction layers at your disposal to make this less painful. Can you explain linear access patterns? A linear access pattern is one where you are reading each byte of memory consecutively without gaps. in order. Like you are reading byte number 0, then byte number 1, then byte number 2, then byte number 3, and that's between 2 points. So for example, one example would be I have an array, I am going to process all the elements of that array from the left to the right, or all elements in a certain index range. And while I am processing these elements, for each array element, I'm going to use all the data that's featured in this array element. So another question, thanks for a seminar and excellent presentation. How much can we rely on the compiler to understand data dependencies and achieve superscalar performance? For integers, it's quite competent. For floating point, you usually need to do it yourself because, again, compilers don't optimize floating point computations very much, mainly because they are not allowed to reorder them. Lionel, the fact that the instruction set architecture is the same for we have instruction set architectures that are common between many processors. Does this mean that binaries are portable from one machine to another? Yes, if you have ever used Windows or Mac OS, you know that you can download software binaries that have been compiled on one machine and use them on another. By default, compilers produce maximally portable binaries, which means that if you compile for the 64-bit version of the x86 instruction set, for example, your programs by default will run on every CPU that has been made by AMD and Intel since 2002. The drawback of this is that you cannot use any new instruction set extension that has been introduced since 2002 by AMD and Intel. And for this reason, compiler provide you with command line options that you can use to say, actually, I'm not interested in targeting all CPUs. I only want to target CPUs that support, for example, the AVX instruction set extension. And if that's not a good enough trade-off for you, then you can also take this decision at runtime by compiling multiple versions of your code, each targeting different CPU generations, and then at runtime querying which CPU your code is running on and picking the right version of the function. I would like to have the slides after the presentation. Is it possible? Yes, we will put it online both on the agenda and on the replay website of the Grace Code School, which is a work in progress. Thanks for the presentation. Is multithreading just a legacy trick from the time where CPU had only one single core, or could it be useful with multi-core? That's a complicated question. Let me go back to this table maybe. So multithreading is still useful today if you have programs that spend most of their time waiting for inputs, but must react very quickly when some input comes. You can think about audio processing applications, web servers, that sort of high-frequency trading in finance, that sort of stuff. If you have this kind of workload, then hardware multithreading is still useful because it allows you to switch to a task very quickly as soon as it gets some new input. If we are talking now about computational operations where the CPU does not spend its time waiting, but mostly, just keeps crunching numbers as fast as possible, I would say that these days multithreading is less and less useful. And there is actually evidence of this because if you look at newer CPU designs like from the ARM HPC CPUs, like NVIDIA Grace or Ampere Altra, you will find that they do not have hardware multithreading. They completely drop this, and I guess their point is that if you have enough superscalar parallelism inside of each thread, you actually do not need hardware multithreading to keep your compute units busy. You can do it all with superscalar code.
From Lionel, what is the meaning of basic in the cell tuning work SCMD in the table, page 16?
So by this I mean there are some patterns for which SCMD is particularly easy. Like let's say, for example, you are doing linear algebra in mathematics, and you want to sum all elements from, you want to compute the sum of two large vectors. This kind of computation where you take two arrays of numbers and you compute a third array that's the sum of the elements of the two original arrays is very easy in SIMD. The compiler can do it for you. And the only thing you need to care about is supporting all the various generations of instruction sets and not being limited by memory bandwidth as usual. This kind of stuff, it's a bit of work, but it's not a huge amount of work. If you are trying to do anything more complicated with SIMD, like even, computing the sum of the elements of an array in SIMD already is difficult, because then you need to take matters into your own hand to make sure that the sums are carried out in the right order. The compiler will not help you. It's much more difficult.
Okay. Arnaud is asking a comment maybe on the similarities between CPU and GPU that you mentioned at the beginning. And please, for me, I ask you the question, don't spoil my talk on that, please.
That's difficult because I'm going to spoil a bit of your talk,
Yeah, a bit, you can a bit, but not everything.
Okay. So let's look at the various hardware topics that we have discussed. This concern of having memory that's a lot slower than compute also exists on the CPU and GPU, and the order of magnitude is the same. You need to do about 100 operations per memory transfer on GPU as well. GPUs also have memory hierarchies. They are a bit narrower. Typically, you have registers, level 1 cache, and shared cache, and then you have the GPU memory. And sometimes in more advanced application, you also need to access the CPU memory, which is even further away from your GPU. But the general concept of a memory hierarchy remains. The general principles of caches also work for GPU. You also need to care about spatial locality, temporal locality. On GPU, there is something a bit different, which is that you have more control on what is cached using a programming abstraction called shared memory. So you can reserve some subset of the cache for your application and tell yourself to the hardware, okay, I want this operation, I want this data to be put at this location of the cache. So you have a bit more control because you can split your cache in one part which is manually managed, but there is still one part which is automatically managed for which this is relevant. You still want to have linear access patterns. You still want to avoid shared memory communication between threads via writes. You still have pipelines. You still have pipeline hazards. You still have data dependency problems. You still have latency hiding. And as I mentioned, on GPUs, you have less resources to hide latency, so you need to be more careful. You still have SIMD. It's hidden in the GPU programming model, but you have this notion in CUDA, for example, of warps, which are groups of threads with neighboring indices. And if you look into what this is at the hardware level, actually, these are just SIMD instruction units badly hidden. You still have superscalar execution. You have lots of hardware multi-threading combined with some local variation of multi-core. So yeah, as you can see, and you still have this notion as well that some operations are faster than others. You still have weird hardware behavior, lots of it. And you still have silly compilers that don't optimize your floating point computations. So basically, I mean, GPUs are just CPUs with different quantitative trade-offs. They have different cache sizes, different superscalar widths, but the general principles are basically the same. And so many optimization patterns that work for CPUs work with GPUs as well, with some adaptations to the orders of magnitude.
Yes, the best example for that is the matrix multiply or the matrix vector product or stuff like that. If you do that in your computation, CPU and GPU, they are the same. You don't have to worry about that.
I actually have a table which takes every word of technical vocabulary from Intel CPUs and translates it into the matching word of technical vocabulary from NVIDIA and back. Because I keep getting annoyed by the fact that GPUs do the same thing as CPU but put different names on everything. So I'm going to attach that to the replay page along with the talk later on.
Okay, a question from Anton. Do CPUs have some kind of auto detection whether data are zero? Do they skip the operation?
In some limited cases, yes. For example, Intel CPUs are known to have an optimization where if you write sequences of zeros to memory, it's faster than if you write any other content to memory. And also, I mentioned before that CPUs can have issues with subnormal numbers. And if there is someone in the room who knows that 0 is a subnormal number, they may have get worried. Don't worry, there is a special case for 0, which is processed as fast as a normal number. So it's quite limited, but we have some of those optimizations inside of CPUs.
I think it's over for the question, and we're on time. It's great. So thank you all for joining us today. Next week, we will talk about computing precision with Vincent and Hadrien also. So don't miss this one. And have a good day. Bye.